All right, let's get started, and folks will come in. Good afternoon, and welcome to another of our distinguished seminars. This time, it's my honor and pleasure to welcome Madhav Marathe, our speaker for today. Madhav wears many hats. He's Distinguished Professor of Biocomplexity, the Division Director of the Network Systems Science Advanced Computing Division at the Biocomplexity Institute and Initiative. He's also professor in the Department of Computer Science, all at the University of Virginia. His research interests are in network science, computational epidemiology, AI, foundations of computing, and high-performance computing. Over the past 20 years, his division has supported federal and state authorities in their efforts to combat epidemics in real time, including the H1N1 pandemic in 2009, the Ebola outbreak in 2014, and most recently, the COVID-19 pandemic. Before joining UVA, he had positions in Virginia Tech and Los Alamos. He's a fellow of IEEE ACM, SIAM, and AAAS. We're looking forward to your talk, very timely. And so please take it away, Madhav.
Thank you so much, Manish. First of all, I want to thank you all for the kind invitation and the kind introduction you made. I've known you, of course, for a long time, but I've also interacted with Chris and Valerio, and David, of course, is here, but Yarden, who I've interacted and worked with and written a couple of papers. So very fond memories. And Matt Seymour is a colleague of ours in the School of Medicine, I believe. I don't quite know the appointment exactly. But so it's a pleasure to be back at Utah. I wish I was there in person. It's a beautiful place, and hopefully I'll get to do that. But let's start the talk. I want to start by, first of all, acknowledging the team and the funding agencies. Fair to say that this would not have happened because of just myself, but many, many folks over a large number of years have worked with us, and also the funding agencies, including NSF, DOD, and such. So my sincere thanks to them. In fact, I think as time goes by, my contribution becomes smaller and smaller in the entire effort. I've provided a few references that folks might find of interest later on. There's some tutorials that we have done. There's a COVID-19 resource page that we maintain. We were fortunate to get an NSF Expeditions grant last year, and we have a web page for it. And also NSF has funded us to set up a virtual organization for pandemic preparedness. And I'm hoping many of you can join us in that goal. So let me start with some just basics of epidemiology, because I think it'll help set the stage up, and then we can move to a detailed model. So a classical model in epidemiology is called the compartmental mass action model. It's a model that has been around since early 1900s, actually. Kermack and McHenrick started this work, and before that, Sir Ronald Ross used this, at least in a somewhat informal manner, during his investigation for the malaria outbreak in many parts of the world. And the basic model is really a set of simple differential equations. You break the population into compartments. Here I've shown you 3 compartments, S, I, and R. And individuals move from one compartment to another compartment following the rate equations that are shown here. S stands for susceptible, I for infected, and R for recovered. Now, of course, as people have moved forward, they have added new class of compartments to it. In COVID, for instance, you need a compartment to capture asymptomatic infections. But this basic simple model is very powerful already. And turns out is the workhorse of epidemiologists for these 100 years for multiple reasons. You can still compute fairly quickly. You can get very good insights from this model. It captures the basic structure quite well, and it's extensible by adding new compartments, changing some of the coefficients. So the concept of effective R or R naught that you all have heard, reproductive number, comes by solving this, and it turns out to be beta divided by gamma, because you can solve these equations and assume that initially S was 1, and you get to solve this equation for steady state. Even as late as last year, these models have been used in very influential publications, and I'll say a little bit about it. Just want to show you how people have gone about extending these models. So on the left is a model that we have extended in our work, where you have 2 strains, and a susceptible individual can go to either I1, infectious state 1, or infectious state 2, depending on which strain the person gets infected by. They recover, but now the person who is recovered from the first strain can get infected again by the second strain. That's why you have R1 going to J2 and R2 going to J1. And then you finally get into a complete recovery mode here. Now, you can, of course, have feedback cycles, which is what is shown in the second automata here, something that Shadi Shadroy and his colleagues, Simon Levin, Brian Grenfell, and others, wrote 2 very influential publications last year in Science. So this middle automata captures the natural immunity and secondary infections. So SP and SS allow you to capture different levels of susceptibility. You start from SP and you go to one of the infected states, followed by recovery, but then you come back to a new susceptible state S with a certain rate, delta. And this is because you are waning immunity to the disease. On the right side, you see a slightly different form, which is where you have vaccines introduced. And again, you can extend this model. So you can already see that even simplest model that Kermack and McKendrick studied, with the addition of these states, can start making the model somewhat more complicated and progressively harder and harder to solve, but nevertheless very popular. Of course, another way to look at it, and there's a reason for looking at it this way, is to view the spread of diseases on social contact networks. And this is the direction our group has taken over the last 20 odd years. Our basic hypothesis is that social contact networks where nodes are individuals and edges capture interactions. Depending on the disease, these edges can change. So if you are having an airborne transmission, you have a certain kind of edge. If you have a sexually transmitted disease, then you have an edge, which denotes a physical relationship, and so on and so forth. If you have a mosquito-borne disease, for instance, then there's no direct edge between 2 humans, but you have it through mosquitoes back to humans. So the basic idea being that, after all, our societies are not as homogeneous as the SIR model assumes to be, and the network captures the inherent heterogeneity in the system. And it's turning out that that's becoming more and more clear to modelers, because an epidemic in, say, Utah is very different than an epidemic in Virginia. And even within Virginia, the epidemic is very different in the northern part versus southern part versus the coastline, and so on and so forth. So let me explain how the model works. It's a really simple model in terms of basic definitions. You have a network. Networks have nodes as agents, humans, maybe animals, depending on the disease. Edge represents interaction. And here you have a number on each edge, which represents the probability of transmission. In this particular example, red node is an infected agent to begin with. All other nodes are susceptible, but have not been infected thus far. The red node tries to infect each of its neighbors, V1, V2, and V3, with probability half. It's a statistical model. It tosses a coin, tries to infect V1, tries to infect V2 independently, tries to infect V3. If it infects them, one of them turns to be in the infected state. So here I've shown you a simple progression of the disease where the nodes recover after one time unit. They don't have to in general. And in this process, at time 0, V0 is infected. In time 1, it infects V1 and V2, but not V3. In time 2, V1 and V2 end up infecting V4 and V6. In the diagram, it's not obvious who infects V4. It could be either V1 or V2. And then finally, V6 infects V3, and then the disease basically stops. So V3 is not infected by V0, but V3 is infected by V6. And V5 never gets infected in this particular system. And this can be written down in a very natural manner as a sequence of configurations, much like we are used to in Turing machines as computer scientists, where one in this, the left table shows that the first node is in state I, all others are in state S, then the state of these nodes changes. Think of this as reading the tape for Turing machine, where each of the symbols really tells you the state value or contents of the tape cell. The right side on the bottom shows what's called a transmission tree or a dendrogram. It tells you how the disease really moved to the population. So here it shows V0 infected V1, V2, V2 infected V4 and V6, and V6 infected V3. I have not shown that here. Good. So the model is really simple, isn't it? But you'll see what makes it really hard to solve this. So let's study a few algorithmic questions. I think this will give you folks some sense of questions that might be of interest to computer scientists, at least theoretical computer scientists. I know Blair is there in the computer science department, and she certainly would care about such models. So here is the basic structure. What you really are interested in is the representation that you're given at the middle and top, the graph and the process. And what you're interested in understanding is the properties of the ensuing Markov chain. So here I've shown a fragment of the chain. The middle, and this is shown at the bottom, where each node here now is a configuration, and then edge labels or weights represent the probability of transition from one Markov chain node to another Markov chain node. The crucial part is, even when nodes can be just in 3 states, individual nodes, when you have n nodes, the Markov chain has size 3 to the n. And in general, edges are roughly, makes it into a complete graph. It doesn't have to be, but it's a fairly dense chain itself. So the algorithmic problems come down to analyzing this chain itself, and that's what makes it very, very hard, right? Because you have an exponential blow up in terms of representation. If you're given the problem and form the chain, then there's not much to do, but that's not a natural representation at all. And that's where the problem lies in the first place. So I'll talk about a couple of interesting algorithmic questions, and I'll tell you what the results are, just to set the stage up and to tell you that these problems are, first of all, very interesting. Second, somewhat non-trivial. And then it will motivate us to talk about real-time epidemiology. So here's the first problem. It's the classical computer science problem, the reachability problem or the state assessment problem. You start the chain at time 0 in an initial condition. You know the transmission dynamics, and you're interested in understanding where the system would be after t time steps. Think of this as understanding if the disease dies out or it reaches a certain endemic state if you have a SIS model. And since the system is stochastic, you are really interested in understanding the probability of reaching such a state. As you can imagine, this problem is non-trivial for the reasons I told you before. And you can actually show this provably, that the problem is actually number p hard. What is more interesting is number p hard even for short time scales. So you cannot really say anything meaningful about predicting the state's probabilities after even a few time steps. And the reasons are exactly what we talked about. So simulations really have to be done. You really don't have a chance to analytically solve this. I find these problems interesting. David is online, and that's why it's important to mention that, from a network science perspective, we have interest in structure analysis of network, which is of interest itself. Then there are time-varying networks or dynamic networks, which makes the problems harder. And now you have dynamics over networks, such as this one, that makes the problems even more harder and more interesting. And I think these can be viewed as next generation dwarfs or templates for trying to understand how these supercomputers might behave. Here's another problem that is quite closely related. It's a forecasting problem. And again, without going through the definitions in this particular case, let me just say that the forecasting problem turns out to be hard too, but there are some easiness results you can get for some special cases. For instance, estimating the overall chance of a node getting sick, a single node getting sick, or a subset for a short period of time. The forecasting problem is related to the reachability question. We just finished a paper, and this paper is going to appear in the proceedings of the National Academy of Sciences in the next few weeks, hopefully. But the important part here is that these problems, the hardness stems from the Markov chain analysis that I talked about. And the forecasting result is interesting because all of us and other teams have been actually still engaged in forecasting the epidemic dynamics. The result says that if you want to get provable results for forecasting using network models, then it's unlikely that you'll be able to find them. Let me end the sort of theoretical discussion with one other problem, and which we'll discuss at length during the practical side of the story, the vaccine allocation problem. Again, the problem is not very hard. You're given a network, you know where the disease started. In this case, let's say the disease starts at a couple of different nodes. That's when you say detect it. And you're interested in trying to vaccinate very few folks to try and reduce the impact of this pandemic. And you measure the impact as the number of nodes that finally gets infected, right? You can, of course, also measure the impact as number of nodes vaccinated plus number of nodes infected. So in this particular system, it turns out that the optimal set is shown in blue, marked in red contour lines, but the solution we might pick might be slightly different. So the point here is that, again, this problem becomes very hard. For a very special case, when the transmission probability was 1, me, Anil, and Arvind Srinivasan, along with others, were able to show that you can get a bi-criteria approximation for this problem. And it turned out that this problem was open for a long time for p-values. The transmission probability is less than 1. Recently, Anil, Arvind, and their colleagues have been able to crack this a little bit by getting a polylogarithmic approximation using some really nice techniques from sample average approximation from stochastic processes. And their paper is, I think, so going to be published very soon. So what are the challenges now in terms of putting all this into practice, which is the main focus of my talk today? I've outlined 5 challenges. There are others. The first one is computational. I've already talked about it. Most of these problems are hard computationally. So, we need to think about efficient heuristic solutions and simulations. The second challenge is the data that is available is very sparse, noisy, and lagged. As a result, the algorithms that we need to design have to be robust. There's a very interesting result that Simon Levin and his students proved, where they talked about flattening the curve, but they found out that if you take very, very good and optimal strategies that basically try and react exactly when you think they should put the intervention in place, given the noisiness, they might miss the boat effectively, and you might end up making problems somewhat worse. Third challenge is near real time. As this pandemic is evolving, decisions need to be made in near real time, often with conflicting objectives, and I will give you some examples of it. But this turns out to be an important question. Implementable interventions, which means theoretical ways to say find optimal set of nodes to vaccinate, really is not very useful, right? Because you can't really decide these 30 people have to be vaccinated and nobody else. It doesn't work for policy reasons, fairness, the network itself is noisy in the way we have made it on the computer, and many other reasons that you can imagine make this somewhat hard. And last, and I think the hardest problem to me in trying to understand epidemics is the coevolutionary nature of this. Fundamentally, our behaviors, the epidemic dynamics, and the social network, they co-evolve. So unlike, say, physical systems, where largely, if you understand, let's say, weather, or then you might be wrong in your predictions, for instance, but you really can't change the weather, at least in most cases. So the error potentially is just a lack of understanding of the physics or not having enough computational power. But here it's not so. It's much closer to the stock market, for instance, where we might think that the disease is slowing down. We might change our behavior and start going out, interacting more. That in turn will pull this disease up. And then that feedback might lead us to taking care of more interventions and controlling it. So you really have to understand this is a Markov decision process where actions and disease are adapting to each other. So let's discuss how we go about trying and sort of addressing this problem in practice. What we have done, and this is a program that now is almost 20 years old. COVID has certainly brought in new challenges that I will talk about. And that's why I have fond memories of working with Yarden early on during 2005, 2006 timeframe. But the way we do it can be broken down into 3 simple steps. The first is to make a digital twin of the region that we want to study. We want to build a digital twin of the social contact network, let's say of New York or Virginia or Washington. We actually started doing this under another project long time back when we were at Los Alamos. This has now become a full-fledged project. And I'm happy to tell you that we can actually build a really pretty good digital twin now of the entire US, 300 million nodes and about 12 billion edges. Now, the digital twin is specifically made for epidemic dynamics. If you wanted to study traffic, it would be slightly different in this particular case. Making this twin is a project in itself, requires lots of different data sets, from census data to data on building locations and built infrastructure, to understanding the kinds of itineraries people have, where they travel, how long they spend their time, the family structure, and new data that is becoming available through phone, GPS mapping of phones can be used here. We didn't have it when we first started, but now we have a couple of different streams, including data from Google. We published a paper on that, which is aggregate flows between zones, and they have ensured that the privacy is maintained. The data from SafeGraph that gives you similar kind of data set. And there are other companies that will give, Cubic is another one that gives you a data set of this kind. So all those data sets get used. In second step, we build a modeling environment, understanding the social and epidemic diffusion processes. How would the disease spread on the network? How would behaviors adapt on the network? For instance, whether people wear masks or not, whether they take vaccines or not, understanding the policies that go in and the compliance along with those policies. And last, you use this modeling environment that is built on top of these digital twins to try and study a realistic question and do the analysis and produce meaningful insights. I call them epidemiological workflows, and these workflows are essentially powered by the large-scale agent models and associated AI and machine learning tools. I want to point out that these systems have a couple of important features that are, I think, central. One is the system is extremely heterogeneous, and that's really the central aspect of it. If you try to homogenize it, then you've really lost the fun in a certain sense from these systems. Now, there might be ways of building aggregated models, but we don't know how those aggregations will happen yet. Equally, in physics, there's a well-known concept of renormalization groups where you try and aggregate systems, but the symmetry allows you to do it in a provable manner. Here, we do not know those kinds of symmetries yet, and that's an open question. The second aspect is that of multiple scales. Just like problems in physical systems, you have scales from there are social scales where you have individuals, families, communities, block groups, counties, states, and nations. But you have temporal hierarchies as well in terms of how fast the person can get infected, how fast the virus mutates, how fast policies are put in place. And then you have spatial hierarchies as well, which is basically a small tract of land all the way to national boundaries and international units. So this multiple scale, again, is an important portion. Throwing these scales away would destroy the fundamental nature of this problem. The last part, before we start going through some good examples, is to try and make the digital twin context specific. So, of course, when we were studying questions for the DoD in 2015, 2016, maybe even after H1N1, we would make up a simple scenario, use the digital twin, and then answer it. For instance, what would happen if you vaccinate some people? But in the initial conditions really were not known. So one would essentially have to make up these initial conditions based on the basic scenario that we had set up. But now the system, as for instance, in the case of COVID, is evolving in real time. And if you want to study what would happen in the future, or want to do even a retrospective analysis, you need to try and put the digital twin in context. So you need to understand the specific of the disease. You need to understand the case and serology, surveillance data, the kinds of interventions that were put in place, the vaccine supply, their schedule, the geography, the hesitancy, and the surveys around it. All this information has to be pulled together to essentially instantiate the digital twin, so that then you can do meaningful projections or retrospective analysis. And I will give you a couple of examples of it. This turns out to be a really massive and interesting data science project, where we need to constantly collect data from 3,100 counties for all sorts of information. Some of it is now aggregated by other folks, but still much of it remains relatively hard to get. And also the formats are different, they're time lagged. Really interesting data science question that we can talk about, especially when you look at the scale and the temporal granularity and speed at which this has to be done. What sort of workflows can this then support? We have actually done quite a few ourselves, and others have done more of them. But when we first started, we studied risk of importation of disease to US and other parts of the world. We then started forecasting the future course of the pandemic with and without interventions. We have been studying resource augmentation problems, for example, building field hospitals, treatment units, resource sharing like ventilators and such. We have then studied questions related to economic impact analysis. We have 2 papers that have been published on understanding what's called the primary impact of the pandemic, and then secondary and tertiary impact of the pandemic on the industry. And then we have also studied the question of projecting healthcare demands, use of PPEs, use of ventilators, when would you run out of supplies? In some cases, we saw this happening in parts of our country. In Texas, for instance, we had a somewhat challenging time during the Delta wave. And finally, counterfactual scenarios that I'll talk a little bit more about. So we've not been doing this isolation. We started working on the COVID-19 part of this from about January, February or so. We started tracking it in late December. We all wished it would go away. In late February, we constituted a team, about 80 of us here at UVA, as well as our collaborating partners. And we've been at it for now, when I made this slide, it was 50 plus week. It has gone to 80 plus week. I can't imagine that's how long it has been. But it's 80 plus week now of constant briefings and analysis. And I think at this point of time, it's fair to say that some of the staff and students are exhausted, but I think, and we are hoping that this will slow down. We have supported a number of federal agencies doing through our work, notably DOD, DHHS, CDC, NSF, NIH. We have supported our state. We are the primary modeling group for our state. We provide weekly briefing to the Department of Health, to the Governor's Office, to the Department of Emergency Management and Department of Education. And we have supported local agencies, hospital systems, the universities, including our own, and the local universities, VCU, James Madison, and such. So the support has been fairly broad. It has been really scientifically very, very interesting, but also challenging sometimes because of various reasons. So here is just one example of the kinds of reports VDH puts out. DOD reports are not online, unfortunately, but VDH reports are all online. Every week, they produce a series of reports based on our presentation. These are just some of the reports. You can go to their website. Essentially, we produce data products and presentations, which are then converted into these kinds of reports and turn out to be quite useful. They are, from literature surveys to situation assessment to model projections and narrative summaries. All of it gets produced as a part of this. We also produce dashboards and decision support tools. Very early on, we produced the surveillance dashboard, just like the JHU dashboard, which is very popular and very nicely done. We also got a lot of traffic with our dashboard, and we continue to maintain it. It tries to get a sense for how many infections or deaths and other types of epidemiological relevant parameters across the world. Many people have used this. We also have a medical resource demand dashboard. You can go to a state and it tells you, based on the models, what sort of demand should you expect in terms of hospital beds and if it might overshoot or not. We have a dashboard that we made for our state called the COVID-19 Mobility Impact Dashboard. This one is not open for obvious reasons. There are sensitive aspects along with it, where the state officials can actually study how they could close one or more of the facilities or partially close them and look at the impact of it. This was done with our colleagues at Stanford, Uri Leskovic, Serena Chang, and others. We actually got a KDD Best Paper Award for this just a month back. A lot of interest in this particular topic. And we have recently released another dashboard called the VaxStat dashboard. It tells you the status of vaccination, the hesitancy, how it's being tracked into various parts and projections as well for this. There are a couple of others that I don't mention. One specific one is to collect interventions that is being done with Stanford right now. So let me give you two examples. Manish, we have about 15 minutes, you think? Yeah.
Yes. Yeah. If you have 15 minutes, take your time.
Okay, good. I think this part might be of interest to folks. So I have taken two fairly large examples of things we have done to show you that this whole discussion is not abstract, but it's really been put into practice. I'll take forecasting, and then I'll talk about scenario projection. And in that, I'll take vaccine prioritization as a very particular example. So let's talk about forecasting. Back in 2010, after the H1N1 pandemic, CDC and NIH put together a program where they pulled teams together to try and develop forecasting methods for infectious disease outbreaks. It was largely contained for influenza. We also worked with IARPA. So many of the teams at least had basic models that were put in place, which were then adapted for the COVID-19 forecasting work. It turns out that unlike weather forecasting, the modeling itself is of course complicated. The physics, to the extent of the physics of epidemics, it's not so clean. The universal laws don't exist in the form that we're used to in physical systems. But as I said, the co-evolutionary nature is hard. Measurements are quite complicated, and we have not built out a sensor system of the kind that we need over time to try and do a better job with this forecasting. So all that means is that the data we get to drive these forecasting systems has a lot of backfill and revisions, a lot of outliers, a lot of noise in it, but nevertheless, we do want to forecast because it turns out to be useful. The data is used at a county level. In fact, the first 4 months, we had to scour the web to get data, but since then, New York Times, CDC, and state health offices have started making such data sets available, and now you can get a good number, but still with some lag for it. So there are two big forecasting hubs, one that the EU or European Union CDC maintains, and one that is maintained by Nick Reich's group at UMass, and it's done for the CDC folks, but everybody in the country can participate in it. And initially started with about 5 or 10 models, but in fact has grown to almost 100 different models that are put in this hub, and they produce an ensemble from this. Some of the models that are more prominent are models from Columbia that Jeffrey Shaman leads, models from Alex Vespiniani's group, models from IHME that all of you have seen, and a few other models, including models from UCLA and others. So we also contribute to this. We are probably one of the 4 or 5 groups that produces information at different scales. We first produce information for 1, 2, 3, and 4 weeks ahead forecast, but we also produce it at the level of a county, at the level of a state, and the level of the whole country. Most models don't do that because the structure of their models. Here we are able to do this in a meaningful manner. And here I've just shown you a picture of how these models track in time. The way we do our work is we actually produce an ensembling method ourselves. It's a super ensemble, which takes a number of different models, simple statistical models like autoregressive models and Kalman filters to deep learning models and mechanistic compartmental models as well. All of them are combined into an ensembling technique, Bayesian ensemble technique, and then the outcomes are provided back to the CDC and to our state, and also to now European Union for most of the European countries. And we just started a project with India with groups at ISC, Princeton, and CDEP. And we started providing weekly forecasts for Indian states as well. We would like to grow this program so that we can have global numbers very soon. We have basic structure in place, I think. The part that I want to highlight beyond the quality, which I will come to, and the complications, is one of an operational pipeline. And this is really putting AI into operational use and doing it over and over and over again. So we started working on this now since about June of last year. August is when this timeline, initially we were doing it really essentially one-off, but the pipeline became operational in August. And then every week we collect all the available data from various sites. This data is processed, is fed to calibrate the models, checked, and then we produce forecasts out on early part of the week, and then this forecast is sent out to CDC, European Union, and now to India, basically. So it's a 1 week cycle. Every week this has to be done. And you might hope that once it's automated, there's not that much work, but it turns out not to be the case, because oftentimes, suddenly somebody will stop producing certain kind of data, or you'll have a lag in it. You'll get strange, spurious noise in it. We also have models that need to be updated all the time. The epidemic in June of last year was not the same as fall of last year, was not the same as December of last year, and on and on and on. So models have to be adapted because the old models really don't make sense as we go forward. So this has been a very interesting exercise. Our models have usually been one of the top 5 models across the board. Columbia model has done very, very well, I must say, and applaud their work. Very consistently done well in this process, but we have stayed in the top 5 or 6. It's an interesting experience. And I want to show you why the ensembling technique that we have built out turns out to be useful. So this plot is somewhat busy, but let me try and explain. You should read it in clockwise direction, starting from top left. And it tells you a couple of different things. We have the models shown in different colors. So AR, ARIMA model, a spatial autoregressive model, Kalman filter, and others. If you see a color on a county, that tells you that particular model dominated, was the best in the ensemble. So when you look at it in September 2020, you will see a particular frame of colors. You move to November, you see a different set of models dominating. In December, a different set of models, and in January, again, a different set of models dominate. The reason is that when the system is relatively stable, statistical models actually do quite well. Initially, the neural network models actually had a lot of hard time because they didn't have enough training data. They have started doing better now. The models that do well when you get a sudden spike are models that are based on, which are causal models, effectively, are basically compartmental models that try to understand the disease dynamics itself. So we have this interesting situation where different models perform well in different parts of the epidemic process. And that's why ensembling them almost always produces rather the best results that we can hope to obtain. We have also done comparisons. As I said, models do reasonably well for most part. One of the metrics that was developed as a part of this hub is called the interval score metric. The idea was that you want model to predict well, but you also want to keep the variance somewhat low. So if you might have a prediction, you might say, I have a very high variance, and in which case, if the real number falls within the ball, then you have done well. But that's not a good metric in some ways. You want a tight ball around it, and this particular metric tries and captures it well. Let me move to the second part, which is potentially as interesting or even more interesting, which is scenario projection modeling. So what's a scenario projection problem? It's a problem of, which can be stated as follows, roughly speaking. You're given a current set of conditions on the ground and a set of possible future scenarios, what might happen. The goal is to assess the likelihood of the epidemiological outcomes for each of these scenarios by analyzing these simulations that we built, or people might have other models. Let me give you a couple of examples. When we started working in December, the big question was to understand the efficacy of allocating vaccines when there are relatively few vaccines. And this is one I will elaborate more, so we'll talk about later. In February, the question shifted to how the vaccine stockpile could be given out to different states based on the progress that they're making in assigning, giving vaccines out, or the prevalence numbers, and would that make any difference? In April, we first started studying the impact of the new strain that was emerging and its impact on the outcomes. From there, we moved in June to understanding the impacts and risks of vaccine hesitancy and reduced non-pharmaceutical interventions. People were essentially exhausted with staying at home. July, we tried tracking multiple strains. In August, we studied the problem of impacts from waning immunity, both from vaccination and natural infections. In September, the studies were done to understand the impact of vaccinating 5 to 11-year-olds. In October, we're starting to study the long-term endemicity issues that go with this. So you can imagine almost every month, the scenario projection that is being done by our team. And it turns out to be rather challenging because you need to run these national scale models. In the projection, in the forecasting work, we did not use an agent-based models. They just became impossible to work with for every week at some point. But we use a slightly more coarser form agent-based models that are called patch models, where we treat each agent as a county rather than each individual. But we work at that level of aggregation to speed up the computation. But this scenario projection part is a really interesting one, has to be done really real time. And I'm happy to tell you that I think after a fair amount of work by the team, we have what I would think a first operational pipeline to support scenario projections at a national scale using very detailed models such as the one I talked about. And the new part here is twofold, two or threefold. One is the pipeline actually uses two different supercomputing systems. One here called Rivana and the Bridges supercomputing unit at Pittsburgh Supercomputing Center. We get modest allocations on it, but non-trivial ones that we use. And at this point of time, we can run 400 replicates of a national scenario, which has about 300 million nodes, 12 billion edges, and about 1 trillion interactions over 200 simulated days on about 9 to 10,000 cores spread out between the two machines in about 33 hours. So it's a, for people who are used to doing physical simulations like MD, molecular dynamics or fluid dynamics, this might sound like a large number, but it's a really significant reduction in what could be done before, especially when you realize that the code base is not at all fixed. As you already saw, every month, the questions were slightly different, and we never anticipate these questions in that particular form. And the models had to be defined every step of the way. So every month, when the questions are posed, the models itself need to be refined further and extended. We think that if we got most of the bridges, we could pull the running time down to 6 hours or so. What this number doesn't capture, which I think is even more important, is the human productivity part. And the reason that is important to me is that the team members had to really initially, before this pipeline was operational, had to spend their own personal time, manage and watch for these systems. Systems would go down, the competitions would go down. And as a result, we would take at least a factor of 2 or 3 more over the basic computation time to finish the work. Because, for instance, a machine might fail to produce results at 2 o'clock in the night, and then we would just find out in the morning. A person X might be responsible for it. By the time the person X finds out that it is not his responsibility, but Y's responsibility, you really start getting these cascades. So I think that the human intervention part reduction and improving human productivity is really important for these hybrid systems. And I'll say a little bit more about it. Just to let you know that this work was not done in isolation. This was briefed to a number of senior level folks, first of all, to the White House by the COVID-19 response team. It was published in a number of papers. Senior CDC officials constantly look at this. And then, VDH and NSF and others. For instance, the ACIP committee committee that looks at immunization practices and finally decides on whether to vaccinate or not, took into account the results that we had produced for vaccinating 5 to 11-year-olds. So it's been very satisfying in some ways to do this. Now, many of this, we are not the only team in this part of the hub, but for NSF and VDH and DOD, we are the only group that do it. For others, this is part of their ensembling effort. And I really want to thank folks who have run that ensembling hub, especially folks who are coordinating it. This also produces a huge and interesting data science problem. You have to initialize the digital twin, as I said, with 3,000 odd, time series tells you how many folks were sick in each of these counties. A typical factorial design ends up yielding between 6 and 10,000 simulation instances and produces 2 to 4 terabytes of data at the output side, which then has to be compressed because we don't need all the details, and then pulled back to our local cluster from the other clusters to try and make sense out of it and produce reasonable plots and visualizations. And I wish I had Yarden here because he would have done a much, much better job in visualizing this on our side. Hopefully we can work with him as we get some time. I want to give one last example and then we'll stop. This is on vaccine prioritization, one of the very early scenario projection works we did. And I personally still like this work. This has proved to be important and useful. This has not been implemented in the US and most countries for reasons that will become clear, but I genuinely believe this is an important technique to try and control the disease. And it's actually intuitive and simple. So the question is this: I have very limited vaccines. How should I allocate them? Now in US, this is not an issue anymore, but if you look at the world, most of the world is not vaccinated. So based on purely an age or immune levels, it might take a while to pull the disease down. So a natural heuristic is to essentially vaccinate them based on social interactions, degree-based heuristics, it's called. And this is not new, right? Folklore suggests that degree-based heuristics should work well. People have done some basic analysis, but there's some important differences during COVID. First, most of the theoretical analysis done before was done for highly structured and random networks like small world or scale-free networks. Doesn't apply to the social networks that we are talking about. Perhaps more importantly, it has never been tested in time-varying realistic social contact networks where interventions were being adaptively put out, where people are adapting their behavior, but also the vaccines were not available to you at the very beginning of the process. It's becoming available to you in small amounts every week. So the question then is, how do you estimate people's degrees and how to find high degree nodes? And we'll come to that. So we set up a fairly detailed design using the components that I described earlier and carried out this study. And our key findings were, and this time it was done using Virginia, but we think the results will hold in other states. And more importantly, right now, in places in say Africa or India where enough people have not been vaccinated, and that remains to be a real potential concern for all of us. But we find that targeted vaccinations like this can reduce the infection substantially. This was done for Virginia at that time as a template, as I said. It would also reduce hospitalizations. It would reduce the deaths by a significant amount. And these network-based strategies can significantly outperform age-based and other strategies that people have been talking about. So the question is, how do you make them operational? How do you measure the degree? But first and foremost, our results are actually take this problem one step further. We show that we don't have to estimate the exact degrees in the social contact network for individuals. We just need to get a reasonably good estimate of the degrees. And even that suffices to produce very meaningful and powerful outcomes. And these results continue to hold when NPIs or social interventions are relaxed, when the new variants come in and they're more transmissible, resource-challenged countries where vaccine might be in short supply, and high incidence rates that might need to be controlled rapidly. So here's a graphic of what I said. We compared the strategy with the base case, which is no vaccination, then with targeting old individuals and then targeting high degree individuals, and it reduced. Now, of course, what is perhaps more interesting, and people might argue, is that people are usually immune compromised. So you might want to give these vaccines to folks to reduce deaths and hospitalization, which actually turns out to be true. But in the long run, by vaccinating others, they reduce the chance of essentially spreading the disease within the families and might reduce the overall impact, which is what is shown on the right side. This plot tries and argues about the impact of these things even with estimates of the degree. So the y-axis here tells you how the estimate is done, or tells you, say, the top one, which does the best in this case, where by reduction of infection, you have been able to estimate degrees very, very precisely, at least in the computational experiments, and you get the best bang for the buck. But even with estimation of degree, which is erroneous, where people who have high degree, but not the topmost, but even within the first 60% of the individuals are given randomly, you actually get a significantly better outcome than purely giving it age-based. And this truly was intriguing because the impact of high degree nodes in a social network was intuitively clear, but this result showed how important that is. The fairness and other considerations are important. We can have a discussion about it after the talk is done. But I think this is a strategy that certainly can be adopted in certain resource poor countries. One way to estimate these degrees, and we, as I said, is we do need to estimate only approximately through digital contact tracing apps. And this can be done actually rather easily without essentially messing up anything with has to do with privacy constraints. You can actually measure these counts of how many people might be close to you and essentially announce whether you fall in the top degree bracket, not giving out the exact number, or medium degree bracket or not. But other way to do this is to build simple correlation models, which we have done, and ask a bunch of questions to individuals. You can actually say certain sort of folks have higher degree, and this is not something we need to be discovering. People who are, people who say interact with a lot of folks, usually in say bartenders or people who in the grocery stores or doctors. All of them belong to this class, and actually you can essentially estimate their degrees in this approximate manner by just looking at their type of work they do. And we think that by doing that, we will be able to reduce the impact of this disease very well. So there are limitations of this because you might expect the high degree nodes to have already been infected, but we know that you get recurring infections. So this still matters. It is important to also know that vaccination nodes does get impacted. And there's a small chance that the nodes can, in fact, still transmit. And so people don't want to become complacent after vaccination. So I want to take the talk to a set of concluding slides. I'll start by the first one, where I wanted, I think it's important to note that epidemic science in real time is a real challenge. And there's a beautiful article by Feinberg and Wilson, which calls to action in building tools for it after the H1N1 pandemic. And we think that the pipelines we have shown you today take the first steps. There's a lot of work to be done, but really important first steps in that direction. But the other parts that I want to stress is that network epidemiology is really a beautiful area for the research for computer scientists, data scientists. It's a goldmine of combinatorial problems, and it's really a good way to look at problems in epidemiology because it captures the network effects much, much better. We also find that doing this work, one has to really work closely with stakeholders. Building models that are explainable and transparent is important. Otherwise, they don't usually get used or can also lead into misunderstanding and in long-term, a lot of problems. We've also found in our work unusual effectiveness of transdisciplinary team science. The SCI Institute is essentially an institute like ours, and I think working with very diverse backgrounds of individuals has been very helpful. A problem that I want to highlight is social, political, and economic considerations during a pandemic are at least as important as the biological process. In fact, I would argue that right now, controlling the pandemic is relatively straightforward if these problems can be solved. And final point is that communicating the results needs to be done in a thoughtful way. We have talked to the press many a times, we've talked to others, and it's sort of important, it's important that as scientists, we try and communicate the results as precisely, but with all the caveats and assumptions that they are not misleading and need to be thoughtful and deliberate as we communicate this. And I'll end by saying that climate change might make matters worse. This is really I would say a stage rehearsal in some ways for a bigger problem that might be coming our way. But the climate change issue actually bring in new epidemiological questions such as antimicrobial resistance and synthetic pathogens. So with that, I will stop. Thank you very much again for listening to the talk, and I'm happy to take questions.
Thank you, Madhav, for a brilliant talk. It's really wonderful to see how impactful this work is. That's a lot of great pieces that came together. We already have a hand up, so we have a virtual round of applause for Madhav, and then I hand it over to Chris for the first question.